Let's talk a little bit about temperature and kinetics here, okay? Concept zero really for this is that you gotta get the pen color here, right? Blue pen, man. Okay, concept zero is that heat is the motion of atoms, okay? So if you have a gas where it's hot, right, the atoms are moving fast, and if the gas is cold, the atoms are moving more slowly, right? This is concept zero, right? We have to understand kinetic theory, right? If you look at this, this is the Boltzmanns formula, right, for kinetic energy, and what it does is it just simply states that the average kinetic energy is proportional to the temperature, okay? And what's interesting here, by the way, is that this 3 that's in there actually comes from the X, Y, and Z directions, right? There's 3 dimensions. If this is a diatomic gas, I think that's a 5, and if it's not a diatomic, I think it might be a 6 halves kBt, right? Okay, which is kind of a cool thing. So Boltzmann's constant is just the ratio of the gas constant and Avogadro's constant. So it's 1.38 times 10 to the minus 23rd. This is the average kinetic energy of an ideal gas particle, right? So ideal, by the way, is, a lot of things, right? The particles don't take up any room, but it's also monatomic, right? And there it is, right? And then don't forget that the kinetic energy is also 1/2 mv squared, right? So there's a whole exciting genre of problems where we can say 1/2 mv squared is 3/2 kBt, right? And then also we can actually figure out the speed that these particles are going, right? So that'll of course be the next thing we do here, right? So what is the RMS value of a helium molecule in the thermosphere that is at 1800 degrees Celsius, right? And of course the temperature has to be kelvins, right? So my temperature is 273.15 plus 1800. What is that? That's like higher math. So isn't that that'd be 2073 or something like that, right? So 2073.15. That's my T, right? And then we want to know, ultimately what we're going to do is we're going to go 1/2 mv squared, where this is the kinetic energy of the mass, and the velocity, right, is 3/2 Boltzmann's constant, right, times T. Okay, so what is the mass of a helium molecule? Well, a helium molecule is 4.003 atomic mass units, right? And each one of those is this, right? So the mass of a helium atom in kilograms, right, is 4.003 U's times, I just looked that up on a periodic table, right, times 1.661 minus 27th, and that's kilograms per U, right? So let's do that too. Times, all right, here we go. And that's not very much. That is 6.649 times 10 to the minus 27th kilograms, right? Okay, so here we go. All right, so now we've got some things that go in there. I think the only thing we don't really know is what this velocity is. So let's just plug it in. So you go 1/2 6.649 times 10 to the minus, right, times the velocity squared that we don't know is 3/2 Boltzmann's constant, 1.38 times 10 to the minus 23rd, right, and then our temperature is 2073. All right, so let's see if this works out here. Okay, so I guess I start on this side. I go 3 divided by 2, 1.38 e minus 23 times 2073. Okay, now divided by 0.5, divided by the mass that I just got. And that's v squared. And then if I square root that, I get 3592, my velocity is 3592.8 meters per second. So the answer at the bottom, you don't always go by that answer at the bottom, right? Okay, 3592.8 meters per second is the speed, right? So that's super fast. Something that's kind of interesting about this, right, is that, of course, helium does not occur in great concentrations in our atmosphere. Most of it, and I think all of it, comes from alpha decay. It's like nuclei will just spit out basically what's a helium nucleus, and then it picks up some electrons, right? And what happens to helium as it gets into the outer atmosphere, that's its RMS value. That's the root mean. That's what RMS stands for. I'll talk about that in a little bit here. That's its RMS value, right? There's going to be some particles that are going super, super fast that actually will be able to, that are even going faster than that, right? They're not all going that speed. That's just sort of like an average, right? So some of the particles get up into the thermosphere where that temperature is that high, right? And they escape. They actually can escape into space. So because they're so small, because the mass is small for a given temperature, the velocity has to be really high. Small particles have to go faster, right? So helium and hydrogen escape Earth's gravity, which is kind of a cool thing, right? Presumably, Jupiter, which is made of hydrogen, is either leaking it very slowly or has more gravity, right? So it's harder for it to escape. All right. RMS, right? And then this is if we do that, this is the Maxwellian distribution of molecular speeds, right? So this is the relative number of particles, or the probability of finding a particle going that speed, right? And then this is the speed, and then this thing goes way out there. It's an asymptote, right? So there are, we figured out the RMS one, but there's a fair number that are going twice that fast, 3 times that fast, right? It really is an asymptote. Notice that V probable, that's just the highest point. That's the most likely speed for a particle to have. Notice how RMS is slightly skewed to the upper end, and that's because RMS stands for the root of the mean of the square. So whenever you do an RMS, it always skews toward the high end, and that's because, let's just take 3 numbers, 3, 4, and 5. Right, the mean of this is 5, right? 3, 4, and 5, the mean of that is 4, right? The average of that, of 3, 4, and 5 is 4, right? Okay, but if I take the root of the mean of the squares, well, let's square them first, right? 9, 16, and 25, right? 3 squared, 4 squared, 5 squared, right? That adds up to 50, right? Divided by 3 is 16 2/3, right? And the square root of 16 2/3 is more than 4, right? And so RMS values tend to skew toward the higher end, and that's because when you square them, the higher numbers tend to contribute more to the square. I think that might be all that we would say, right? And then, of course, as temperatures change, like this is 0 Celsius, right? At body temperature, which is 310 kelvins, right? Notice that this thing moves down and it kind of scooges out that way, right? Which gives us even more asymptote like that, right? So the hotter it is, also the more you get this sort of asymptotic nature where this upper end is inflated like that. The velocity to escape from the thermosphere is about 10,000 meters per second. Okay, we just figured out the RMS velocity there is 3,000, right? So that's going to be right there, right? Well, easily there's things going 1, 2, 3 times that fast. There's a fair number that have escape velocity. It's a bit like watching people at a skating rink. There's always some kids that are going super fast, right? The vast majority are going some speed like this, right? Anyway, I think that's it.